Okay, so our fundamental rules for charges, which is opposites attract and like charges repel, is modeled with Coulomb's law. And basically, Coulomb's law gives us the mathematical equation for how charges interact with one another when they're placed near each other. So here's the equation for Coulomb's law, but I'm mainly going to just refer to it as electric force. All right, so Coulomb's law tells us the amount of force that these charges will exert on each other. All right. Remember that opposite charges attract. Attract is pull, and pull is a force. And like charges repel. Repel is push, and push is a force. So the attract and repel is here. There's our force. And I put this little sub E for electric force. Okay. Now you see the equation. Hopefully a lot of you recognize something familiar about it. It looks very similar to Newton's law of gravitation, all right? We have our force, we have K, we have object 1, object 2 over R squared, all right? Now, what do these things represent? K is similar to big G for Newton's law. It is a fundamental constant of the universe. Basically, this gives a ranking of how strong the electric force is. Now, we saw a demonstration in that the electric force dominates the gravitational force in terms of strength. We saw we could pick up packing peanuts with a few extra charges, and those extra charges totally dominated the strength of the Earth. All right. Now, the reason why that happens is because of the value of K. The value of K is 9 times 10 to the 9th. Now, there's a whole bunch of units here, but I'm not worried about those now. All right. So 9 times 10 to the 9th, that's a humongous number. And if you compare that with Newton's law, big G is 6.67 times 10 to the negative 11. So the constant in this universe, the electric constant, which we call K, is a tremendous number, tremendously bigger than big G, and that's why electric force is so much stronger. Now, if you remember back to Newton's law, you had Fg equals G m1 m2 over r squared. Well, now instead of m1 m2, we have q1 and q2. Newton's law of gravity was determined by the amount of masses. All right. Well, Coulomb's law is determined by the amount of charge. All right. And so Q is the amount of charge for each of those things, okay? And this R squared here, R is the distance between the objects, all right? The distance. Now, we use R instead of D, and that's not a big deal, all right? Don't think you have to cut this in half like it's a radius and you're comparing this with a diameter. It's not that. It's the same thing as Newton's law of gravity. It's just the distance between objects. And notice that distance is squared, all right? So just like Newton's law, this has the same format. We call this an inverse square law. All right, so that's the equation. Let's see how we can use this thing. Okay, so in this first example problem, we're just getting used to the idea of this inverse square law, how this law tells us how these charges behave. And you notice they're not giving us that much information. You're just saying, well, what happens if we do this? What happens if we do this? How we approach those problems is we take our equation that governs what's the interaction, and the first thing we do is we put in ones for everything. Even K, I know K is a number, but let's just imagine it's 1. We'll put in 1 for everything. So in a normal situation, we would have 1, all right, a force of 1. Well, in the first problem, it says what happens if everything stays the same and all we do is double the distance? Well, we're going to keep everything the same except double what we need to in the equation. So it'll look like this. So we just put in Fe. All right, we keep everything 1 that hasn't changed. K didn't change, we didn't change the charges, but we did change the distance between them. Remember, the distance between them is R. And if we doubled it, well, what's double 1? 2. But notice in the equation, 2 gets squared. So once we plug that all in, we get 1 over, the 2 becomes squared, and we get fourth. And then we can compare these two numbers. What it was originally was 1. All right, we'll assign a value 1. I don't know what that means literally. But how much did that change? Well, it's now a quarter of what it was. It was 1 divided by 4. So if we move this thing twice as far apart, if we move these, so let's imagine the charges are here, and then we move them twice as far apart, the force doesn't double. All right, the further away they go, the less they can act on each other. All right, and that kind of makes sense. But it's not just a 1-to-1 ratio. You can see that we doubled it. The force wasn't cut in half. The force was cut by a fourth because it's an inverse square law. If we double the distance, well, that distance gets squared, and we're left with only a quarter of what we would have. All right. Now we go to the next part B of that, right? Obviously, we can compare it to if everything was the same, we'd have an FE of 1. But now we're going to triple the distance. So we have FE is equal to everything that we don't change gets assigned 1, because that's what it was over here. Everything was assigned 1. But now the distance is 3 times. But remember, in the equation, that 3 is squared. In the equation, this isn't squared, that's not squared, that's just K, that's Q, and that's Q. But R is squared. So when we do that, remember 3 squared is not 6. We're not multiplying these two things. 3 squared is 9. So now if you tripled the distance between those, we took them 3 times further apart, it would be 1/9 of the force they were feeling. So what this means is, let's say these two charges would have, let's say if they were, whatever they were, they had a force of 90 newtons acting between them. If we tripled the distance between them, that 90 would be divided by 9, and we'd only get 10. All right, wouldn't it be 90 divided by 3? It'd be 1/9 of that. All right, and then likewise in the final problem, or in the final example, right? Remember, we would have FE, our original would still be 1. Everything goes as 1. But then FE on the final example, K is 1. That didn't change. The charge didn't change. And, yeah, sorry, the charge didn't change. But now we moved them closer. Well, if we move these charges from here to here, they're going to exert more force on each other. They're closer to each other. So we would get 1 on top. But remember, the half would be squared, so we get 1/4. 1 over 1/4, see that down there, 1 over 1/4 would be 4. And we can see now that's 4 times. So yeah, they came half as close, but they didn't just become twice as strong, they become 4 times, because it's a square law on the bottom. So if we come closer, we get stronger. If we go further away, we get weaker. All right? So, and not just a 1-to-1 ratio, it's squared. So that's how we deal with an inverse square law, and that's kind of what Coulomb's law and Newton's law of gravity tells us. All right, so in this example problem, they've given us a couple things here. When we read through this, they tell us the charge is a Coulomb. Now, Coulomb is the SI unit for charge. All right, and we abbreviate that with capital C here. So it said for one charge had 3 coulombs, we put that big C. The other one had a charge of 5 coulombs. All right, and the distance between them is 2 meters. That's what I wrote down here. So at this point, you just plug and chug everything that you have. All right, so they want to know the electric force between them. So that's just FE. We know K is 9 times 10 to the 9. And we multiply it by 5. Sorry, Q1 is 3. The other charge is 5. And we divide that by 2 squared. And we go to our calculator at this point. And we get 3.375 times 10 to the 10. And since it's force, it is in newtons. All right, now the last part of this, though, is we have to tell the direction. Force is a vector, so we have magnitude and direction for any vector. There's the magnitude, all right? Now the direction is very simple here. All you have to do for a Coulomb's law is, for the direction of the force, is determine whether it's attract or repel. Now, how do you do that? You look at the two charges. These are both positive charges, so that means like charges repel. So to finish out your answer, you would just notate that it would be a repelling force, and that'd be your full answer. All right, let's move on to our last example with Coulomb's law. Okay, in this problem, you see something a little different in there. They gives us two charges, one positive and one negative, all right? But that has that funny symbol, and it looks like mu, all right? In other words, we have Q1 is equal to 6 microcoulomb. Now, first thing you're going to notice is I didn't put a negative here. So in our E and M stuff, from here on out, all our equations, there will never be any negatives plugged into the equation, all right? How we do this is we plug in all positive numbers, and then to get direction, we get a direction afterwards by doing some sort of technique. For this one, it's just determining whether they're attract or repel based on charges. So we never do any negative numbers. Now, the other thing is you see we have mu in here, like our coefficient of friction. But that is actually a prefix, all right, a metric prefix. And that means micro. It looks like a squiggly, weird looking M, but that means micro. So we have to convert that. That's a common prefix in our Coulomb's law. Notice in this problem here, we have a huge, that's Coulomb's law. Because when we use our regular Coulombs here, 1 coulomb of charge is a lot of charge, all right? And we usually don't deal with that much charge, all right? So our microcoulomb is a little bit more sensible. So how do we convert that? It's very simple. You just write down our first one, and this micro literally just turns to times 10 to the negative 6. So this just literally gets written as that. And it's that simple. And then we just put our coulombs there. So there's our Q1, and therefore our Q2 is 8 microcoulomb, which just means 8, and the micro turns into times 10 to the negative 6. All right, now once we had that, we can go right into our equation. Fe equals 9 times 10 to the 9 times 6 times 10 to the negative 6 times 8 times 10 to the negative 6 all over the distance between them, which is what is the distance between them? Distance between them is just 0.5. Remember, that's squared. All right, and then we go to our calculator. Okay, and our calculator gives us Fe equals electric force between them. In other words, how much they're pushing or pulling is 1.73 newtons. Okay, that's a magnitude. Now, don't forget to give the direction. How do we do that? Well, we just look at the charges. Now, notice here that it's a little annoying because I put them both positive, but read the problem. One's a positive, one's a negative. They are opposite charges, so they will attract each other. So then I would just write attract. And the reason why we do this is because it tells us the direction that both charges are feeling. They are both being attracted to her. If they're repelling, we know that they're both being pushed away. All right, and that's how we do our basic Coulomb's law. That's how we can determine the electric force between them. That's how we can determine how much a charge attracts or repels another charge. Okay?